Before we begin, any questions? All right. So far, as I discussed, we've been mainly looking at deriving tail bounds on random variables and basically linear combinations of random variables. And in the last class, we were trying to derive tail bounds, or we were going along the lines of trying to derive tail bounds on arbitrary functions of random variables, right? And these are of interest in various applications, such as let's say bounding the largest eigenvalue of random matrix, or bounding the maximum degree of a random graph, and so on and so forth. Right? So in trying to do that, we were first trying to bound the variance of an arbitrary function of a random variable. And we saw that functions of random variables, of independent random variables, can be written in a special form. In particular, we saw that the variance could be written as in the following way. It is equal to the sum of expectation of delta I square, or in other words, it's a sum of variances of delta I, where each delta I is basically obtained by taking the variance. So let's quickly recall the definition of delta I. Delta I is essentially Zi minus expected value of Zi, which is expected value of f of x1 through xn, but each of these is taken only with respect to xi plus 1 up to xn. Minus the expectation with respect to xi xn of f of xn. Correct? So we can, unlike sums of independent random variables, where we can write the variance of as the sum of individual variances. In this case, we can write the variance as the sum of variances of these so-called deviations. Correct? And our goal is to use this to derive something stronger, and that something stronger is this Efron-Stein inequality. It says that if x1 through xn are independent random variables and have bounded variances, then, and g is an arbitrary function of these n random variables, then the variance of g of x1 through xn can be written as a sum of these expectations square, where this expectation is taken over all the n random variables. But here it is expectation of f of x1 through xn minus expected value of f of x1 through xn, but taken only with respect to xi. Right, so this is equal to summation I equal to 1 to n expectation with respect to xn f of xn minus expectation with respect to xi f of xn the whole square. Right, so if I call this random variable yi, then this is basically the sum of the variances of yi. But we can also write it in a slightly different way. As it turns out, the right hand side can be shown to be equal to this. So if I define zi prime to be the same function, but only with the ith random variable replaced with an independent and identically distributed copy, then the variance of z is basically half of the sum of the variances, or half of the sum of the expectation of z minus zi prime the whole square. Right? And there are other equivalent ways of representing this particular quantity. Now, in particular, let's take an example where the function of interest has the following property, wherein So suppose that f of x1 through xn has the following property, that if I replace any one particular value of any one out of the n different variables, then the function value does not change much. Okay, in particular, if I take this minus f of, I keep using f, whereas I should be using g. Suppose g is a function such that g of x1 through xn minus g of x1 xi minus 1 xi prime. Suppose I replace xi with any other value xi prime, then the function value does not change much. Xn, suppose this is less than or equal to ci for some constant value ci. So for each I, there is a particular ci. If I replace the ith variable with something else, then the function value changes by at most ci. If this property holds, then what can I say about this particular quantity? Yeah, correct. By how much? So ci square, right? Because z minus zi prime is at most ci, right? So expectation of z minus zi prime the whole square can be at most ci square. Right? So for such a function, the variance of z, which is the variance of g of xn, is less than or equal to half summation I equal to 1 to n ci square. Correct? As it turns out, we can improve that constant a little more. It turns out that this is in fact less than or equal to 1/4 summation I equal to 1 to n ci square. And we can get that using the last inequality in the Efron-Stein inequality. Right? Using this, it's possible to get a 1/4 instead of a half. But first, let me just give you a sketch of the proof of the Efron-Stein inequality. Right? So how do we prove this? Well, originally we had something of this form, right? The variance of z is equal to sum of expectations of delta I square. And from this, we want to derive this particular quantity. Correct? So what do we know? We know that the variance of z is basically equal to summation I equal to 1 to n expectation of delta I square. Let's expand delta I out. So what is delta I equal to? It is expectation with respect to x I plus 1 up to xn of g of xn minus expectation with respect to xi xn of g of xn, right? Or I can also write this as expectation with respect to I plus 1 up to xn g of xn minus expected value with respect to just xi g of xn. right? Again, x1 through xn are all IID random variables. So I'm taking expectation. So this expectation is with respect to n minus I random variables, n minus I plus 1 random variables, whereas this is with respect to n minus I random variables. And I can arbitrarily, since they're all independent, I can take the expectation in any arbitrary order I want, right? So I have this. So what is delta I square equal to? It is expected value x I plus 1 up to xn g of xn minus expected value with respect to I xi g of xn the whole square. But what do I actually want to show? I want to show that this variance is less than or equal to summation I equal to 1 to n expected value with respect to xn of g of xn minus expectation with respect to just xi g of xn the whole square. So given that we ultimately want this, can you obtain an upper bound for delta I square? What do you think would be the right way to derive a bound of this particular form? Something much simpler. Well, just look at the expression that we want and the expression that we have, right? So right now the variance is equal to the sum of expectations of delta I square, right? But here essentially I have expectation of delta I square is expectation of square of some expectation, right? So if I were to get an expression of this form, I would have to take the expectation outside the square, so to speak. Can I do that? I guess, yeah, you could use Jensen's inequality, but it follows from a much simpler reasoning. Okay, what is the inequality that you want to use? The square is the formula. Okay. So you take the expectation of, right? We will get an answer. So what you want to show is that this is less than or equal to expected value respect to x I plus 1 to xn of g of xn minus expectation only with respect to xi of g of xn the whole square. Correct? This is what we want. So this is, let's call this is our yi, right? So what we're saying is that expectation of yi square is greater than or equal to expectation of yi the whole square. The variance is always non-negative, right? So so I agree, you can get it from Jensen's inequality, but maybe a slightly simpler reasoning is that the variance is always non-negative. So expectation of yi square is greater than or equal to expectation yi the whole square. Right, just follows from expectation of square is greater than or equal to expectation the whole square yi. is greater than or equal to 0. Well, I'm loosely calling this variance with respect to yi because here the expectation is only with respect to xi plus 1 up to xn. So it's a conditional variance, to be more precise, conditioned on x1 through xi. But whatever. So I have this, right? So what is expected value of xn delta I square is basically less than or equal to xn this way. Right? So from this we get that the variance of g of xn is less than or equal to summation I equal to 1 to n of this square. Okay, so this was straightforward. Now let's look at this particular quantity over here, right? This is expectation g of xn minus expectation with respect to xi g of xn, right? So here we're taking expectation only with respect to xi. Let me now define zi prime as g of x1 up to xi minus 1 xi prime. Basically I replace the ith random variable with an independent and identically distributed copy. So this is an IID copy. So conditioned on all random variables except xi, what can you say about z and zi prime? So zi and zi prime are basically the same, except that they're taken as functions from x1, z is a function of x1 through xn, whereas zi prime is a function of x1 through xi minus 1, xi prime, xi plus 1 up to xn. So if I condition on the remaining random variables, z is now a function of just xi, whereas zi prime is a function of xi prime. So conditioned on the remaining random variables, z and zi are independent and identically distributed, right? Okay. And I claim that this quantity, expectation with respect to xn of xi prime of g of xn minus or let me say zi minus zi prime. This would be I claim that this is equal to two times this the whole square. So let me take two random variables, x and y. They're both IID. My claim is that the variance of x, which is the same as the variance of y, is equal to half of expectation of x minus y, the whole square. So, okay, first, if this claim is true, then this is true. You agree with that part, right? And if this is true, then the second part is also true. That is, this variance is less than or equal to half of summation I equal to 1 to n expectation of z minus zi the whole square, zi prime the whole square. Okay, so let me call this C1.
Expectation is with respect to xi, right?
Which one? Here? This is with respect to, there's no xi prime any longer here. So this is with respect to only xi. So this would be just, so not zi, but expectation of z with respect to xi of z the whole square. So if that particular claim is, that C1 statement is true, then the variance of z is less than or equal to half summation I equal to 1 to n expectation with respect to xn as well as xi prime of z minus zi prime the whole square. Okay, and C1 is true if this particular claim is true. All right, but why is the claim true? Let us look at half expectation of x minus y the whole square. X and y are IID, right? So expectation of x is equal to expectation of y. So is there a way I can get variance? Correct. So inside the square, I just add and subtract expectation of x or expectation of y. So this is x minus expectation of x plus minus y minus expectation of y. Right. So this is basically the sum of the variances of of x and minus y. So this is equal to half expectation of x minus expected value of x the whole square plus expectation of y minus expected value of y the whole square minus 2 times expected value of x minus expectation of x times y minus expectation of y. But x and y are IID, so this quantity is just equal to 0. So this is variance of x. This is also equal to variance of x because they're IID. So this is just equal to the variance of x. Which one? This. Okay, so this is equal to expectation of x minus expectation of x times expectation of y minus expectation. But what is that equal to? That's just equal to 0, right? Any questions? All right. So the rest of it can also be shown in a similar fashion, but I'd like to move on to some applications. So there are these 2 points followed by this. I leave it as a homework. So show that if x and y are IID, expectation of x minus y the whole square, or half of this, is equal to expectation of x minus y, the positive part of x minus y the whole square. And it is also equal to expectation of x, the negative part of x minus y the whole square. And the positive part is basically x minus y. The positive part is just equal to the maximum of x minus y and 0. So it's equal to x minus y if x minus y is positive, and it's equal to 0 otherwise. And similarly, the negative part is equal to the minimum of x minus y and 0. So it's equal to x minus y if x minus y is negative, and it's equal to 0 otherwise. Okay. So let's see a few examples. In particular, try to bound the variance in certain problems where even computing the expectation might be extremely difficult, right? So here's a problem that occurs in operations research, basically resource allocation problems, and it's called the bin packing problem. And the problem is the following. Suppose I have bins all of equal size, okay? And I'm given a number of items which are randomly drawn. And my goal is to somehow pack these items into these bins. Each bin has some sort of capacity, let's say unit capacity. It has a volume of, let's say, 1 cubic centimeter. And I'm given a bunch of items, all of different sizes, less than 1 cubic centimeter volume. And the goal is to somehow pack as many items so that I use as few bins as possible, right? For example, if I have, let's say, 3 items one of size or volume 0.4, another of volume 0.3, another of volume 0.6, and another of volume 0.5. Right? Now, if I try to sequentially pack them, then I would need 3 bins, correct? So the first 2 could go into one bin, the third could go into a second bin, and the fourth could go into a third bin. But that's not the best way of packing them into bins, right? Because if each bin has unit size, then I might as well combine these two and these two into 2 separate bins. So 2 bins are sufficient to pack these 4 items. Correct? So how do we model this problem? I have x1 up to xn, all IID random variables, and each xi takes values between 0 and 1. The goal is basically to pack x1 up to xn into the minimum number of bits. Each bin has whatever size or volume equal to 1. So basically the sum of the xj's which get packed into one particular bin has to be less than or equal to 1. Now you can formulate this as an optimization problem, and that this problem itself has been well studied. It turns out to be a computationally hard problem to solve. And as you can see, even trying to compute the expected number of bins does not seem easy. Right? You don't have a closed form expression for this particular quantity. But even without knowing the distribution on x1 through xn, we can derive a bound on the variance of this particular quantity on the number of bits. Right? So the quantity of interest g of x1 to xn is the minimum number of bins required. To pack x1 through xn. And how would we derive a bound on the variance of this? Suppose I change one particular value of xi, right? I just pick the ith value and I replace it with any other value. By how much can the minimum number of bins change? 1. It could increase by 1 bin or it could decrease by 1 bin, but not more than that. Because I know that each xi is at most is between 0 and 1. Correct? So changing xi can change g of x1 through xn by at most 1. So what can you say about the variance of g? Half summation ci square. What ci is what? It is 1, right? So n by 2. Or I claim it's less than or equal to n by 4 because you can improve that constant to 1/4. Right? N by, but whatever, it's some constant factor times n. Right? So this was easy, right? We didn't even have to know what the actual distribution of x1 through xn was. And we can't really get a closed form expression for g, but then we still have a bound for the variance. If I am able to show that, let's say the minimum number of bins required is, say, sublinear in n, then I can show that with very high probability, g of x1 through xn is going to be close to the expected value just by using, let's say, Chernoff. Sorry, not even Chernoff bound. I just have to use the Chebyshev inequality because I have a bound on the variance, right? Let's see another example. Right? And this is called the longest common subsequence problem. So suppose I'm given two strings and my goal is to find the longest common subsequence between the two strings. So for example, let's take the words recent and say excellent. Okay, I'm not looking at contiguous substrings which match, but basically subsequences that match. For example, is there an R in this? No, you can't find an R, so there's absolutely no match. Is there an E? Yes, there is a match. There is a C which matches here. Is there another E? Yes, there is a match. N? Yes. T? Yes. Right? So this E, C, E, N, T is a subsequence of this particular string. And in this case, E, C, E, N, T is also a subsequence of this particular string, but they're not necessarily sort of contiguous. So in this case, this turns out to be a contiguous subsequence. It's a substring, whereas in this case, it's a subsequence, but not a substring. Correct? And for this particular example, it turns out to be the longest common subsequence. But there could be multiple other common subsequences. So in this case, if I take, let me call this xn, this is maybe yn or ym, g of xn yn is the length, the quantity I'm interested in is the length of the longest common subsequence. And this is, for example, used in version control systems like Git, wherein you're given two files and you want to find the common, the match between the two files. If you've done something like git diff before, or a diff between two files, you're basically trying to compute the longest common subsequence. Right. So, and it's also used, for example, in bioinformatics, wherein you're given two DNA sequences or RNA sequences, and you want to find the longest common subsequence between the two. Okay. So this is the quantity that we're interested in, and suppose that xn and yn are IID substrings, right? IID strings. Xn and yn are IID. So for this problem, it turns out that the expected value of g of xn yn, let's say even if xn and yn are Bernoulli P sequences, the exact value of the expected value, the exact expected value of g of xn yn is not known. There are some bounds known on this. You can't even numerically compute it exactly. But there's a conjecture that it's equal to I think 2 by 1 plus root 2. So expected value of g of xn yn divided by n. This quantity is conjectured to be two by 1 plus root 2, or just Bernoulli half. Right? It's that complicated to compute. But we can compute a bound on the variance very easily, right? And why is that? Suppose I change one particular character in xn or yn, what happens to the longest common subsequence? It changes by 1, right? That's it. And so what can I say about the variance? Variance g of xn by n, this is less than or equal to, so it's summation ci squared by 4, but then just keep in mind that there are 2n random variables over here, so it is 2n divided by 4, so n by 2. Right? But then if I now try to use, say, Chebyshev's inequality to bound the deviation, so the probability of deviation, then what happens? Suppose I want to find what is the probability g of xn yn minus expected value of g xn yn is greater than, let's say, delta expectation of g xn y. Yeah, you have to.
Any random variables to model each letter of the word?
No. So each word is an IID sequence. I mean, so in this case, I've taken the alphabet to be binary. That's the only thing. So this is sort of the simplest case, wherein both xn and yn are IID Bernoulli half strings, right? They're binary strings, and you just want to find the longest common subsequence. What I have given over here is a much more complicated alphabet, an alphabet of size 26. You could put in any distribution on xn and yn. They don't even have to be IID. They could be independent, but they could be non-identically distributed. That's okay. Right? A similar bound still holds. It's some constant times n divided, some constant times n. But in this case, what can I get a bound on this probability? You'd use Chebyshev's inequality here. So what does Chebyshev's inequality give us? Sigma square, which is let's say variance of g divided by delta square times expectation of g the whole square. But this, as we know, the variance is less than or equal to n by 2, and this is delta square times the expectation is n times some constant, some unknown constant. So let me call this constant times n the whole square. So this is some constant 1 over constant times delta square times 1 by n. So this decays to 0 as n tends to infinity. So without much effort, I got a tail bound on this particular topic, right? But it still seems a bit weak because I'm only getting a polynomial in n probability of tail bound. right? Can I improve this? As it turns out, we can. In fact, it's possible to get an exponential tail bound if you have this bounded differences property. That is, if I change the value of xi, if the function value changes by at most some ci, then I can get an exponential tail bound on the deviation for f or g. So this says that if x1 through xn are IID, or let's say just independent, and g is a function of x1 through xn, satisfying the property that if I change the ith symbol, then the function value changes by at most ci. Then the following holds: the probability that g of xn deviates from the expected value by an amount greater than t is less than or equal to e to the negative 2t square by summation I equal to 1 to n ci square. For example, suppose that g is just the sum of the random variables, right? So x1 plus x2 plus x3 and so on up to xn, and each xi is a bounded random variable. It's bounded between minus ci and plus ci. Xi is bounded between minus ci and plus ci. Okay, then you can see that it satisfies this bounded difference property, because summation overall j x1, so x1 plus x2 up to xn minus the sum of these xi's, but with xi prime different, this is just equal to xi minus xi prime, right? And this is at most ci, right? Then what you're saying is that the difference between the sum of the xj's minus the expected value of the sum, the probability that this is greater than t, is less than or equal to e to the minus 2t square by summation ci square. And we've already seen such an inequality before, right? We use the property. This is basically the sub-Gaussian tail bound on bounded random variables, right? The constants could be a little bit different, but we still end up with the same kind of dependence. And what we're saying here is that such a dependence holds not just for sums of random variables, but arbitrary functions for which this bounded differences property holds. All right. I will not prove this particular inequality. I'll give you a reference for this. But in some sense, you can derive a simpler, a sort of a weaker inequality using the Efron-Stein inequality. But just that is not enough to prove McDiarmid's inequality. You need a little more. Okay. Basically, so this in some sense is a sub-Gaussian tail bound on g of xn. You can obtain a sub-exponential tail bound, basically a bound of the form e to the minus constant times t divided by something else, just using the Efron-Stein inequality. But to get this much more powerful inequality, you need a little more, right? We will not prove that in this particular course. But instead, I want to focus on as many applications of these as possible. Okay. So one useful application in estimation and machine learning is this problem called kernel density estimation. So suppose I have random variables drawn from some particular density, and my goal is to estimate this particular density, right? Then what kind of techniques can I use? So for example, if I have an IID sequence drawn from a finite alphabet, then I can just count the relative frequency of occurrence of each symbol and use that as my estimate for the true distribution. And we know that as n tends to infinity, we can derive a concentration bound or a tail bound for this particular estimator. So, but on the other hand, if I want to estimate a density, then what can I do? Because after all, if I take a finite number of samples, it's not going to be enough to very closely approximate the density. I'll have to use something more. The empirical frequency is not really an estimator of the density, because if I take n samples, then with probability 1, all the n samples are going to be different if it's a continuous random variable, right? So then what can I do? One thing I can do is try to compute the histogram, right? And use this histogram as an approximation of the density, right? But the histogram is not a smooth function. So then what can I do? So one popular approach is this kernel density estimate. Okay, so recall the problem is the following. I have x1 through, let's say I observe n samples, all drawn IID with density fx. Okay, and this fx is unknown. So what you can do is you pick a sufficiently smooth function k, some smooth function which is called the kernel. Right? And your estimate, the so-called kernel estimate, is the following function. So it's equal to 1 over n times hn summation I equal to 1 to n k of x minus xi divided by hn. So this is one estimator. Okay. For example, if I take k to be 1 if xi or x minus xi lie in one particular bin, that they're close to each other by some amount delta, then effectively I would get the histogram. Right?
So that would mean k is not smooth.
K is not smooth, I agree. It's some function which is not smooth. But then I can choose other functions k as well. Okay? And each choice of k gives me one particular estimate. And for this particular quantity, we can try to derive a bound on the variance using the Efron-Stein inequality. And using that, we can try to derive a tail bound on how badly the kernel density estimate does in estimating the true distribution fx. Okay, so let's stop here. We'll continue with this example in the next class.